Thank you. I'll probably run over if I'm not careful anyway, so I'll go ahead and get started. My name is Eric Evans. I'm on the Apache Cassandra PMC, have been since pretty much the time it entered the incubator. Working on it originally for Rackspace, then for Akunu, and I work for a company called the OpenNMS group now. And this talk is on virtual nodes, a new feature in Cassandra 1.2. Before I can explain virtual nodes, I need to kind of get a little introductory background at the risk of telling you something you may have already heard in another talk today or at another Cassandra event, kind of basic material. Call it DHT 101. DHT is probably, I probably should have resisted the urge to put that down. The original research that led to this kind of distribution was called a distributed hash table. Fundamentally, Cassandra is still a distributed hash table under the covers, even though our data model is much more richer than a simple hash table. More importantly, it's a content addressable system. And records in Cassandra are rows or collections of columns that are identified by a unique key. And so when we say it's content addressable, we're saying it's the content of that key that determines where within a cluster the data lives. So how we typically visualize this is you take a ring or a clock face, if you will, and you map the entire namespace for these keys in sorted ascending order such that when you reach the highest possible key, you roll over to the lowest. And having done this, if you divide this ring up, or partition it, if you will, then you can give each of these partitions to a node in the cluster. And then finding out where to go write or read a value is just a simple matter of finding where that value, where that key sorts on this ring. That determines the initial location, the partitioning, but we want to store multiple copies. So for that, we just need something that is deterministic and based on that first location. From this point out, it doesn't matter which copy is which. There's no special distinction. This is just how the algorithm for placement works. Oops, skipped that. Okay, so once we have multiple copies of data on the cluster, we have a different kind of problem, which is that these contentious properties between consistency and availability that we usually use the CAP theorem as a device for explaining this, but it's pretty simple. If you imagine we had a replication factor of 3 and we just want to copy data onto it synchronously, we rely on the fact that a successful operation is writing on all 3 nodes successfully. Then we can reason about the consistency of the data on the system, but we've given up availability because we can no longer meet those requirements if we're down a node, if a node has failed. Conversely, if we choose asynchronous replication instead for all or part of those 3 copies, we can get availability because we can survive a node failure, but we can't reason about the consistency. And that's what the CAP theorem is really speaking to, is that these properties are contentious in a distributed storage system. This is the reality we have to live with. So in Cassandra, we deal with this with something called tunable consistency. You may have heard this referred to as eventual consistency, but I think that's less descriptive and it actually has sort of a negative connotation to it. It's tunable consistency because you get to pick your trade-offs between consistency and availability on a per operation basis. So if you imagine, again, a replication factor of 3, if we chose a consistency level 1 for a write, then we're going to wait until we've successfully written it to one node, and then we consider that a success. After we hang up and go away, we're expecting, really within milliseconds, for asynchronous replication to update these remaining 2 copies, but we have no guarantees at that time. So if we did a low consistency write like this, we might follow it up with a high consistency read, a read of consistency level all, at which point we'll find that most recent value if for some reason there's any inconsistency. And you might do this if you really, really valued write availability. and if you have valued write consistency, even at the expense of an error if there was a node down. More common would be to do something like quorum, which is a majority or one more than half. 3 being the smallest replica size, replica count that we can have and still do a quorum. And the neat thing about a quorum is if we use that for a write and we use it for a read, then we can gain read-out-write consistency while still surviving one node failure in the case of replication factor 3. So we have multiple copies on the cluster. We have a way of dealing with, in a very flexible way, these contentious properties of consistency and availability. So it sounds pretty elegant, it sounds pretty nice. And on paper, it does. But in reality, after years of experience using this, we found it's not quite as perfect as it seems. It's not as pretty as it initially looks. So one problem relates to the distribution of requests or operations. So going back to that first diagram, I said that keys that belong on partition A are replicated in the simplest case, on the next successive nodes working clockwise around the ring. So we have data from partition A, node A, being replicated to nodes B and C. But this is true for all of the nodes in the cluster. So node Z replicates its data onto A and B, and node Y replicates its data onto Z and A. So what we have is 3 different replica sets that all share A in common, node A in common. We have YZA, ZAB, and ABC. So then what happens if we lose node A? Well, if consistency level permitting, we can continue serving requests, we can continue reading and writing, and this will all be fine and dandy once the cluster's healed, but these nodes are going to receive the extra load, the load that should have been going to node A for all 3 of those replica sets. So it's localized to the neighboring nodes, topologically speaking. In a perfect world, you'd like to see this distributed throughout the nodes in the cluster, but it's localized. So we could fix this. We bring the node back up, or let's say in the case of a catastrophic failure, we bootstrap a new node in place. Either way, we have data that should be on the node that we missed, and we need to get it copied in. So where does that data come from? It comes from those same 4 nodes, the same nodes that share A in their replica set. And this adds even more load to the nodes that are already receiving more than usual. And so again, this is something you would like to see, the slack taken up by the other nodes in the cluster. Another problem is how we manage placement of data within the cluster. So imagine we have a nice, well-balanced 4-node cluster. Traditionally, this has meant that the operator divides the key space 4 ways and creates corresponding tokens and assigns them to nodes, and then we have this nice balance where each node has the same amount of data. But at some point, hopefully, we're scaling up in throughput, we're scaling up in data, and we need to grow the cluster. And this is something Cassandra is supposed to be good at. It's linearly scalable. You just bootstrap a new node in, right? Except for where do you put it in? The very best you can do is to bootstrap one of these existing, or bootstrap into one of these existing partitions to bisect it. But that creates a pretty severe imbalance. One you'd like to correct. So one option is to just move the remaining nodes such that you position them where you have balance again. But for every one of these moves, there is an interval of data which has to be moved off of the node onto another one and onto it from another node in all cases. So it's a lot of unnecessary movement of data. We'd like to avoid that if possible. So this isn't a really good solution. Which is why we usually tell people just double the size of the cluster. You have 4, double it to 8. You have 3, double it to 6. And this works simply because now we're bisecting all of the partitions. But frankly, I think we got a little bit too comfortable telling people to just double the size of their cluster. it's almost absurd if you think about it. I mean, this could literally equate to doubling your hosting costs. So this is not a very satisfying answer either. So if you haven't figured it out by now, the solution to this is virtual nodes. And virtual nodes, quite simply, is we're breaking that one-to-one relationship between a partition and a node, and we're giving each node, many partitions. So we just divide the ring up into many more partitions than we have nodes, and then randomly allocate them to the nodes we have. And this has a number of benefits. It's operationally simpler because you no longer need to manage tokens. You no longer have to calculate the splits in the ring and assign tokens. You no longer have to move them if there's an imbalance. You just really don't have to do anything with tokens at all anymore. And you get better distribution of load. If a node fails, then all of the nodes in the cluster pick up the slack. And if you have to do a repair or a bootstrap, all of the nodes stream data to the node, to the node being repaired. And this is because while it is still true for each partition that we have a sort of a notion of topologically near or neighboring nodes, each node hosts multiple partitions and they're randomly allocated, so we share replica sets with a high enough token per node count, with a high degree of statistical probability. We share partitions with every other node in the cluster. And this streaming from multiple hosts gives us concurrency. We get to transfer that data from many nodes to the one as opposed to just those neighboring nodes, which makes that faster. And by creating more tokens, by creating more partitions, it follows that they're smaller. And smaller partitions equate to a more reliable cluster. There's a lot of bipartition operations, things that happen on a partition that can be very intensive from a disk network I/O perspective, or computationally intensive. And by making those smaller, there's less to redo if there's an error or a failure of some sort. Things progress more incrementally. And finally, it's a better excuse me, it's a better all right. It's better for the case of heterogeneous nodes because it's easier to just simply give a node fewer or greater partitions, or if it's a smaller or larger node, capacity-wise. So there are a number of strategies that can be taken when implementing virtual nodes, and these names are sort of possibly made up. They may not directly equate to things you see in literature, but these seem to represent what you find in existing systems out there. So these are things that we can draw experience from, as opposed to just maybe academic research. The first of these is automatic sharding. So this is just when you have a partition that is bounded in size. It will grow no larger than X, and when it reaches that threshold, we split it and redistribute the data to nodes with less data. This is how Bigtable, the Bigtable paper describes things. So it's how the clones like HBase and Hypertable work, and I think this is pretty much how Mongo's auto sharding works, although I understand so little about how Mongo works. Then you have fixed partition assignment. This is what's described in the Dynamo paper as strategy number 3. This is the one that they finally settled on. And the way this one works is you divide the ring, the key space, into q evenly sized partitions. You just give it a constant number of partitions. So each node has q over n. It has an equal number of partitions. And when you add a new node to the cluster, you just recalculate q over n and copy that many partitions from the existing nodes to the new one. And finally, we have random token assignment. And for random token assignment, each host is assigned randomly generated tokens, the constant here being the number of tokens per node. So when we add a new node to the cluster, we randomly generate T new tokens. And since the key space is finite, every randomly generated token lands within an existing interval, and that data, corresponding data, is copied off to the new node. This is similar to how libkatama works, if you're familiar with the library for distribution on memcache. And really, it's kind of a generalization of Cassandra when you think about t being equal to 1. Better. Okay, so when looking at these strategies, there's a number of considerations to take into account. One is how many partitions is this going to result in? What is the size of these partitions? And how do these two things change as we scale the cluster, as we grow it in data and number of nodes? More partitions is better, but only to a point. These partitions are metadata that has to be exchanged between nodes. More of them equals greater computational complexity when making routing decisions. Taken to the extreme, you can imagine a partition being so small that it could only hold one key. And that's not where we want to be. And the same with partition size. We would like to keep these things to a reasonable size that we could, that we can make assumptions about how long they would take to transfer and how long it takes to compute anti-entropy, things like that. So it's all about finding the right balance. This table sort of describes at a high level how these considerations fit into the properties of these strategies. I will explain these, though, in greater depth, but that table might be of use to someone later. So for automatic sharding, we have a constant partition size, that being the constant with automatic sharding. And that's good. We can reason about the size of a partition really well, and that's useful. But because the partition size is a constant, it means that the number of partitions scales linearly as we add more data. And for a system that we're ostensibly trying to make infinitely scalable, that's not very good. For the fixed partition assignment, this is the one where we assign Q evenly sized partitions to the cluster up front. Obviously, the constant there being the number of partitions, that's good. We can reason about how many partitions we have. But because that's the constant, the more data we have, the larger these partitions become, which isn't so good. Also, the one problem with fixed partition assignment is there's greater operational overhead because it's on the operator to know or to think about ahead of time how much data is going to be in the system and how many nodes it will take to accommodate that so that they can assign the correct number of partitions up front. And it's rare that people have things that well in hand to start it off. I'm never that well prepared. And finally, we have random token assignment. So random token assignment, again, is we assign T random tokens for every joining node. The constant here being the number of tokens per node. And so the total number of partitions for the cluster scales linearly with hosts, which is okay. It's certainly better than scaling with the amount of data. And the partition's size scales based on the amount of data and the number of nodes. So you add more data, the partitions tend to get bigger, but adding more nodes serves to make them smaller. And so this is really overall like the best fit for Cassandra. And this is in fact the strategy we chose. So that's pretty much like all of the theory, I guess. The rest of it just pertains to like practical details of the implementation in Cassandra, which isn't much because this actually makes things a lot simpler. There's not a whole lot to this. So the only real configuration aspects are found in the Cassandra.yaml file. There's two things that affect virtual nodes. One is the initial token parameter, which will allow you to specify a comma-separated list of tokens. We don't recommend doing this. It was kind of added for sake of completeness. Initial token does something, and there's an expectation there, so it was more or less conforming to the element of least surprise. What we'd recommend you do instead is just set the num tokens parameter. And the default that we're using for that continues to seem like a good choice is 256. It's worth mentioning that num tokens is similar to initial token in the sense that it's kind of a one-shot deal. You cannot change the num tokens parameter later and have that affect the number of tokens on that node. It's set the first time it's run. At some point, we'll probably add the ability to add or remove tokens to scale up the number of tokens scale them down. But that capability doesn't exist now, and frankly, there hasn't been a lot of impetus for it. It's not something you'd want to change lightly anyway. If you're familiar with any of the operational tools, some of these things changed for reasons which may or may not be obvious. Node tool info is something that operators run commonly just to sort of get a summary view of one node. But one field in that output was the token, and obviously this is much less useful if it blows up by 255 lines because you have 255 more tokens than you did. So we just suppress that output and ask you to pass a switch if you want it. The other one that changed is node tool ring. A node tool ring started off as a way of, not very intuitively, but as a way of sort of diagramming that ring that we're so used to looking at in a linear, ASCII fashion. This was meant to describe the content topology of the system. But what it's kind of grown into is this sort of like one-shot, high-level status, like a way of looking at the cluster from a high-level overview. And again, having that output blow up by 255 lines per host means it's much less useful for that. So it's still there and it still does what you expect, but it's if you use Cassandra and you switch to virtual nodes, you'll find it's not useful as that sort of summary view anymore. So we introduced this command called node tool status, which sort of is meant to fill that same role that node tool ring used to be, except for that we have one line for every endpoint. One interesting thing about the output of node tool status is that we display a host ID. It used to be the case, it was an assumption throughout the code base, documentation, best practices. We referred to a node by its token because there was only ever one token. It was the only thing that was globally unique about a node. An IP address could change, but the token is what really represented that node. With 256 of them, for example, if you stick with the default, even with 5, it just doesn't make as much sense. So we replaced this with a UUID, and you'll probably see this start to like make its way into documentation and the administration tools as a way of referring to the node instead of the token. Now, the output of this command also displays the number of tokens that are assigned to each node. Useful information as well. Okay, so you can migrate an existing cluster, be it 1.1 or below, or a 1.2 cluster that you started up. I should mention that by default, Cassandra 1.2 still starts up with one token for each node. At this point, you have to opt into virtual nodes, and this is kind of consistent with how we sort of, take these overarching new features and kind of ease them on to people instead of just throwing it out there and hoping that we tested everything. So even a 1.2 cluster that was started with just one node per one token, one partition per node can be migrated. And the way that works is imagine you have like a 3-node cluster. You simply go into the configuration file. As long as the node has only ever had one token, then when you set the num tokens parameter, restart the node, it will essentially split that token, that partition, num tokens ways, so 256 by default. You end up with 256 partitions that are all within the same interval of the one that you had before. So there's no placement change. All of the data that was there before still belongs there, and all the routing decisions still send everything for that partition to the same place. And there's some value in doing just this because if you went no further, this is really safe. You could do this on a running system. Of course, rolling restart on the nodes because it's just a metadata change. There's no movement in data, nothing drastic happening. And you still get the smaller partitions, so things, the general reliability increases. And over time, we would expect nodes to fail and be replaced. At which point the placement of the partitions, the mapping of the partitions to nodes would randomize over time. But if you don't want to wait for that, there is an operation called shuffle, which will create a new mapping of token to node that is randomized, and then slowly transfer them between nodes. The way that works is the mapping is created, and each node transfers the ranges that are destined for it to itself. So, for each range transfer, there's a source and a destination. We're queuing these entries up on the destination of those range transfers, and then each one works through their queue in order, sequentially, one at a time, with a break to sort of help prevent one node from outrunning the others and copying all the partitions to itself. And to the best of my knowledge, this works, but this is definitely something you should probably test in your own environment first and get your own sense of comfort for it. It is in many ways much more complicated than things like decommission and bootstrap, but it will never really be as thoroughly tested as those things because it's the sort of thing you would do at most once, and not every cluster is going to have it run even that much. So use a little caution. Test it for yourself, make sure you understand what it's going to do. Everybody's got a development or staging environment, I'm sure. They all test everything before you push it into production. So just make sure there's no exception here. Doing a shuffle is pretty straightforward. If you run create, it'll create those mappings, write the moves onto the queues of each node, but it won't start it. You can use ls to view what's going to happen. Clear if you don't want that to happen, if you change your mind, and then enable and disable to toggle that on and off. Maybe you want to run it during off-peak hours and stop it when peak hours come around. The only other switch of interest is the DC or only DC switch, which would limit the remapping to within a single data center. So if you have a multi-data center cluster, and you don't want range transfers to be happening over the WAN link, you can localize these moves to a data center. And finally, I'll finish up with a little bit of performance because I don't know why, it's like a cultural thing. We want to quantify all, everything we do, and how else do you quantify it other than how much faster it made it? And it did make it faster. So this is a benchmark. I forget the specifics. I think we're like 13 M1 extra large EC2 instances and something like 500 million rows. It's not really important. What we were kind of looking for here is the relative difference between Cassandra 1.1 without virtual nodes, 1.2 with virtual nodes. This is the remove node operation. So this is the amount of time on the y-axis that it takes for the remove node to complete. And likewise, here's the difference in the time it takes for a bootstrap to complete. And the reason these two graphs are here, remove node and bootstrap, is that's kind of your worst case scenario if you had a node failure. You have a node that's completely unresponsive. You can't gracefully exit from the cluster. You need to get another one back in. This is kind of your worst case scenario. Between these two things, it's about 3.5 times faster, which is really important if you think about it, not just because it's faster and we all like to see things happen faster, but because in this case, this is how long it's going to take for us to get back up to full capacity, full redundancy, to get the cluster back into sort of 100% state. So 3.5 times faster is definitely a good thing. And with that, I will take any questions if I have the time for them. If you have a question, raise your hand and we'll get you a microphone because we are taping this.
My question is, how does it affect rack and DC awareness with virtual nodes? Is there any difference at all? Or
it makes no difference at all to rack or DC awareness.
So when you're randomly choosing tokens at random, you choose tokens or partitions to put on a particular node, but still the DC awareness and rack awareness by machine? Yeah,
there's no DC or rack awareness taken into account on where to place partitions on machines. The only difference there is that obviously we wouldn't want to put, we're going to skip over the same machine. If typically the way the network topologies would work is you would look for the next. You just keep skipping around to the next token until you found one that satisfied a requirement. So now we're just going to skip over any nodes that are the same node, but otherwise it works the same. It was actually surprising how little had to change to make this work.
So you spoke about how the partitions are divided over all these nodes. But doesn't that affect availability? Now, if you have double failures, let's say for RF3, then the probability that two nodes share the same key is much more now.
Yes, that's true. That's actually a good question. So it is true that with classic Cassandra with 1 token per node, that if you irretrievably lost the right 3 nodes where replication count is 3, you would lose your data. And the probability that you would lose the right 3 nodes with virtual nodes is much, much higher. In fact, probably 1, because again, we said that they all share data. So the answer to that is the same as it is with 1 token per node is, don't let that many nodes fail. But it's actually Richard Lowe with Acuna who worked out he did the math. I'll have to trust him it was right because it was beyond me, but that with the faster rebuild time that provided there was no one asleep at the wheel, that you were statistically less likely to lose data because you could recover faster. I don't know if you buy that argument or not. I'm not sure what the technical terminology for that is. I heard someone call it distribution factor or whatever. What you'd like is somewhere in between. You'd like something that was less than perfectly localized like Cassandra with 1 token is, and something better than completely. But that is a fair point. Yeah, if you lose any 3 nodes, replication factor 3, and you irretrievably lost them, it was gone forever, then you would lose some data. So if that's a problem, use more nodes or don't let that many nodes go down.
Over here, by the pillar, other way. In the case where you have contiguous vnodes, you didn't shuffle, what are the wins that you're getting there that are worth the penalties that you pay from dealing with multiple partitions? For example, the repair case is significantly worse. What are the wins if you don't have random distribution like in the contiguous case?
Well, your short-term win is just that with smaller partitions, again, smaller partitions make these sort of operations that depend on things happening on a bipartition basis more reliable because they're smaller. You do want that random placement. That's an important property. But I was just pointing out that it is worth doing, even if that's all you're doing, because there's essentially no risk in it. And again, I assume that at some point in time, nodes will come up or down, and each time you bootstrapped a new node in, you're going to get that placement's going to be a bit more randomized. But yeah, ultimately you do want to see that placement randomized between nodes, that mapping randomized.
So with the vnodes, how would you manage hotspots? Like with the regular style, you could say, like for example, if you had a hotspot, you could say only this token is on this sort of beefy machine, for example. Now that sort of displacement is randomized, how would you try to manage that?
I don't think, with that many more tokens, with 255, if you use the default, 255 times the number of nodes you have, more tokens, the likelihood that you would have a noticeable hotspot should approach 0. I mean, you would have to have extremely skewed distribution among your in your data in terms of hot keys. I mean, extremely skewed in order for a 3-node cluster, for example, with 768 tokens, to have 1 or 2, and that's kind of your hotspot scenario. You literally have to have 1 or 2 that was a problem, 1 or 2 of those partitions, and it seems less likely, much less likely.
Do you have any number on the repair, how slow it is? I read it's considerably slower than the single partition.
I don't think it's considerably slower anymore. There were a few bugs there that related to performance that got ironed out. I don't know that it's considerably slower anymore. Certainly shouldn't be. I think we found some bugs there. But if you know of something I don't, correct me afterwards or point me at what you're reading.
Any other questions? So with vnodes, is the only thing that you get is just the extra tokens, or are there, like, is the JVM actually split up into 256, separate JVM instances?
No, it's just the partitioning. Still one JVM per node. Yeah. That's probably an unfortunate naming virtual nodes. We continue to call it that because that's what the Dynamo paper called it, and it is the same thing that's described in the Dynamo paper. So rather than confuse things by giving it a different name, it's unfortunate naming.
Just to follow up on the repair, what he said about repair being considerably slower, is repair slower with vnodes? I was confused there.
I mean,
this is anti-entropy repair.
It really shouldn't be.
That's what I was hoping.
Yeah, I mean, there's really, I almost want to say I know that bug, or I remember that bug, and that it was fixed. If you really want to know, we can ask Sam Overton, because I think it was him that fixed it. He'd be at the Kunu booth on the in the corner of the pavilion. We can go talk to him. I think that was fixed. There's no good reason you're right. Yeah. Okay. Thank you.